Hi, today we're going to be doing our first lesson in the very exciting integrals unit, and this lesson is called antidifferentiation. Now, just like with a lot of things in math, I guess I'm going to back up a little bit before I start talking about the notes formally. But just like a lot of things in math, there are like opposite procedures you learn. So, for example, at one point in your life, this was a new problem. Right? And so then you learned how to multiply that out and then get a polynomial, right? So 2x squared, and then it's to be bad if I don't know how to do this. Okay, here we go, something like that. And then you would learn how to factor that. Okay, so you learn to multiply things out, and then you learn how to unmultiply them out. Well, that's true in a lot of mathematics, right? We learn how to do something forwards and then we learn how to do something backwards. That's basically what's happening in this lesson. What we're doing is figuring out how to take something that already is a derivative and then move it back to find what it came from, so to speak. So I'm telling you y prime, I need you to tell me what y could be. And that process is called finding an antiderivative. Now, something that's of interest is that I said an antiderivative, and that was very intentional because a constant has the derivative of 0. And so a 0 in my derivative could have come from any number of different constants. And that means that when I go backwards, I don't necessarily know what that constant is. So my antiderivative is going to actually be a family of functions, okay? And you'll see more about what I mean if that just sounded like blathering idiot talking. I'll try to straighten it out. Okay, so this is actually like the definition that would be in a textbook. And I think the most important thing here is just noticing something with notation. So we know that if we have a function f, and we take its derivative, one way to denote that is as f prime. When we go backwards, we certainly can use that. If I start with an f prime, I'm going to say that I have an f. But what if my starting thing is just called f? Now I need something to denote I'm going backwards. And what we usually will use is a capital letter. Now I'm going to caution you, just as someone who has known me for a long time, I know myself that I am sometimes a little sloppy in my handwriting in terms of writing a lowercase f versus a capital F. So please try to ask questions if my handwriting is confusing to you. Okay, so what they're saying here is just that capital F is an antiderivative of lowercase f if this is true, if taking the derivative of capital F leads you to lowercase f. And then they point out that because of that whole thing I was kind of talking about earlier, this plus c can be any constant. And so, and then they talk, this part over here is just explaining, that the derivative of a constant is 0, and that's why. We need to think about that. But I think it's actually, from a student lens, it's probably easier to understand this with some examples. Okay, so what I wrote in this table was, if f prime is blank, then what is f? So if f prime is 0, then f of x would have to be just some constant, right? Because the derivative of a constant is 0. If my derivative is already a constant, and I called this k just because I knew I was going to use a c in the previous line. So if your derivative is a constant, then your original function, so to speak, would have to be k times x. And then you could have, again, some other constant, because when you take the derivative of what I just wrote in purple, you're going to get k. Right? The derivative with respect to x of that statement is just k, which is what we're saying here, okay? If my derivative is x, well, that must have come from an x squared type of polynomial, but I'd have to have a 1/2, right? Think about the 2 coming down in front, multiplying by that, going down by 1, right? There's going to be my x, and then again, I could have some other constant there. Maybe that constant is 0, but maybe it's not. Maybe it's something else. If my derivative is x squared, well, that must have come from an x cubed statement, but to have just a 1 as my coefficient here, I'd have to have a third. Are you seeing a pattern? Gosh, I hope so. Okay, this last one, x to the third. If x to the third is the derivative, Then x to the fourth must be what it came from. Okay, taking this statement and finding its derivative would lead me to that. Okay, so this suggests to us what the power rule is for antidifferentiation. We certainly had a power rule when we were taking derivatives. This is just going in reverse. So if my derivative is x to the n, then my original function, oh, that looks really bad. Then my original function has to be 1 more than that in the exponent, and then I divide by that. Some people like writing it like this instead, tomato, tomato. Okay, that kind of thing. All right, so power rule is for things that are of polynomial format, right? Your independent variable x raised to n, which is a number, okay? This is your variable. This is a number, okay? And then if you think about it, there's one exception to this rule, which is actually indicated within this practice. So I'm going to give you just a second. Please pause this video and then come back and see how you did on these. There's one question that has a little wrinkle to it, so I hope you find the wrinkle. Okay, so within this, we should have figured out that this one would be 1 over 14 x to the 14th plus a constant. This is equivalent to x to the negative 5. So that means that if I antidifferentiate, I get x to the negative 4. Right? This is equivalent to x to the 1/2. So when I antidifferentiate that, this is my answer. Here's the wrinkle. This is equivalent to x to the negative 1. If I just apply power rule to that, that is going to be problematic because I would end up dividing by 0. However, I hope you recognize that you do know a function that has that derivative. That guy is natural log of x. Okay, and for reasons that we will talk about more in a future lesson, when you antidifferentiate, you actually need absolute value around that x. Actually, I can talk about it a little bit right now. Think about how the natural log function looks like this, right? This is a little picture up here in my pink pen about natural log of x. And so the input, the argument of a natural log function has to be bigger than 0. And there's nothing in this poofy pink cloud that says that x has to be of that big type, right? We could have 1 over negative 3. And so it basically boils down to a domain issue, right? We need to have the argument of my natural log function be positive in order to be something that I can evaluate. That doesn't quite get into all the nuances, but maybe that's enough for now, okay? Over here we have cosine, and so I want to ask myself, what is a function whose derivative is cosine? Well, let's start out with sine and think about that. Okay, is the derivative of sine cosine? Sure is, could have a constant. The next one, we want to think about what function has the derivative of secant x tangent x, and that's secant of x plus a constant. And then this is a sneaky Pete. This is really secant squared. Okay, that's what it is equivalent to. And so what function has that derivative, secant squared? So if the derivative of secant is secant tangent, it's the derivative of tangent that's secant squared. Now, I hope you're bothered right now by the terrible notation on this page, because you can see here I have this and I have this. Those two things are not equal, right? This is like saying this is my y prime and this is my y, and things are not labeled nicely. Okay, we really should work on always labeling nicely. That was a terrible, well, it was on purpose. It was to motivate the fact that we need some better notation. So we need a symbol that says, hey, find the antiderivative. So just like we have notation that's like, hey, take a derivative of this, or hey, take the derivative of this with respect to t, right? We have notation that means take a derivative. We need a symbol that means, hey, take an antiderivative. And that symbol is called an integral sign. Let's take a minute and practice writing an integral sign. Years of teaching have told me that sometimes this is a hard symbol for people to write. I think about the letter S, right? Like if I'm making a letter S, and then I just elongate it, right? Like make the hooks very small, okay? And that helps me to make a good integral sign. That's what it's supposed to look like. Typed, it looks kind of, I don't know, I don't love the, format of that, but, Google Docs. You do you, Google Docs. Okay. The symbol used to indicate finding an antiderivative is called an integral sign, and it looks like this. This part is here to tell us what our independent variable is. So that part is just saying with respect to x. And the reason that that would matter is, let's say I had 2 as my integrand. That's what you call it. The part inside the integral is called the integrand. If I have the integral of 2, without having anything after it, I don't know if that's 2t plus a constant, or 2x plus a constant, or 2y plus a constant. All of those are possible antiderivatives depending on what my independent variable is, right? If it was this, that would be my answer. If it was this, 2 dx as the integrand, 2x plus c is my answer. And if this is my integrand, then that's my answer. So this part needs to be there to really tell us what variable we're even working with, okay? And then when we find that integral, that's called integration, okay? It can also be called antidifferentiation. So here we have our power rule from earlier. Remember the power rule that we kind of wrote slopshotty up here, right? This was our power rule. This is the power rule just written with an integral sign, same thing. Okay, and when we find these integrals, they're called indefinite integrals, okay, because this is not a definite number, okay? There's going to be other reasons why it's called indefinite integrals. Yes, indeed, there's something coming up called a definite integral. Get psyched. So there's going to be other reasons, but for now you can think of it as being indefinite because we don't definitively know which member of the family of functions we want, okay? So that this box is stolen off the interwebs, and it's just an illustration that if I'm anti-differentiating this expression and I know I get some cubic, by having different values for c, we end up getting different curves in a family of functions, right? They all have the same sort of shape. That's why they have the same derivative, but they're just slid up and down in the coordinate plane, okay? Some basic things about integration: if you have a constant multiplier, you can pull that out of the integration sign. That sometimes is helpful. If you have adding or subtracting, you can split those up, okay? That is not true for multiplication or division. Be cautious, okay? All right, so these are just your trig derivatives in reverse, so none of this should be like new or shocking, right? We know that the derivative of, we know the derivative of sine, we know the derivative of cosine, et cetera, et cetera. These are just stated backwards, right? Like the derivative of tangent is secant squared. So the integral of secant squared is tangent plus a constant, right? So this is not new math. This is just saying things backwards, okay? And then we're going to do some examples here that I did not bring to where I'm recording this. Well, that's fun. So that means right now I'm going to stop recording, and then this is going to be a 2-part video. That's fun. Yay, fun.